Good, we're done. Okay, let's begin. Thank you. Welcome everyone to the Astronomical Society of Edinburgh. If you're a visitor, I think we have some visitors in the room, welcome. Slightly different tonight is our speaker is in Canada, so we'll be watching him on the screen here, but he's live on a Zoom stream that we have. So it's July, so we often get a lot fewer people here in the hall, but we still have a lot of our members on Zoom as well. So this is what we've got coming up. I've got a few slides, some news items, what we've got coming soon, and then the main event of the evening is Dr. Brad Gibson telling us about stellar winds, givers and takers of life. So I'll introduce him after the slides. And Nigel Goodman's going to be telling us about the sky in July. AZARO, if you don't know, is our remote telescope in Spain, the ASE Remote Observatory, and some of the data that's been coming out of there recently is rather amazing. I think we had it fully working for a couple of hours last night. As you know, we've had lots of trials and tribulations with it, lots of tweaking and so on, but it's working pretty well. This is taken with the 12-inch Mirror telescope, the Crescent Nebula. And what's interesting is our members process the data and they all do it in slightly different ways. That one's from Matt Finch, that one's from Mike Christie, that one is from me actually, that one's from Pat Devine, and that one is from John Briggs. It's all the same data, hydrogen alpha and oxygen 3, and it's false color anyway, so we can interpret it however we like and however we want to bring out the details. But
well, what is that object?
Crescent Nebula. Crescent Nebula. So yeah, lots of stuff happening with AZARO, as you can see from our Flickr group. We've been doing the Crescent Nebula, Propeller Nebula, some dark nebulae, Dumbbell Nebula, and so on, lots of galaxies. So yeah, if you're a member, please grab hold of the data and have a go at processing it yourself. And that's how the telescope was looking this morning. As always, Alan Pickup has written our Sky Guide, and he's done that for July 2024, and that is on our website now. And he says that we've had a bit of a shortage of planets in our sky for a while, but Saturn, Mars, and Jupiter are starting to reappear again. So have a look at that. Alan is the font of all knowledge when it comes to Sky Guides. A little bit of news. We are going to be ramping up our observations of what's become known as the Blaze Star, T Coronea Borealis. I always like to temper expectations in that it won't ever be amazingly spectacular in our sky. It'll be a star that wasn't there before in Coronea Borealis, as bright as the brightest one in there, but what is actually happening in the system itself with the red giant dumping lots of matter onto this white dwarf from the accretion disk, when it actually pops, it's quite an amazing process that's going on. I think it's a recurring nova, happens every about 80 years, I think it is. So the experts say any day now. I think it was April plus or minus 3 or 4 months, so we're almost at the end of that period. So we are going to be ramping that up. We'll be using our telescope in Spain, but Pat Devine is going to be telling you a bit more about that in the newsletter on Sunday. And if you're using your own telescopes, your sea stars, you should be able to do some monitoring of that as well. And the BBC are interested in talking to us about our campaign on that, so we might get on the news. We're almost at our August break, so we'll be closing down for August, but we've got 2 meetings left. On the 12th of July, next Wednesday, we'll have our Imaging and Observing Group meeting. That's online on Zoom. That's for our members only. And on the 19th of July, the last of the session, one of our honorary presidents, Professor Catherine Haymans, Astronomer Royal of Scotland, will tell us about the universe, reality or simulation, and she'll be there for a question and answer session after that as well. We'll close down for August, and then the first meeting back on the 6th of September, we'll be back here again, a hybrid meeting, shedding light on the dark side of the universe with gravitational lensing from Dr. Benjamin Gibbon. That's it from me, so if we can stop our share here, over to Brad Gibson in Canada. So thank you, Brad, for joining us, and over to you, please.
Well, thank you very much. I I certainly do appreciate the opportunity to chat with you on this special anniversary for the ASC. It's does mean a lot to me, and I like to feel that I'm a little bit Scottish as well. My great grandparents are from Edinburgh, so even though I was not born and raised there, a little part of my genetics are tied to Scotland. So really is an honor to be a part of the program for 2024. Very much appreciated. And I really apologize doubly for not being able to be there in person, as I've sort of alluded to with when the invite came through. I'm my mom is going through some challenging healthcare here in Canada. And so I've been trying to spend as much time as I can over the last few months here with her, supporting her through this unfortunate process that we all end up having to go through at some point in time. So I do appreciate the opportunity to take a break and spend an hour chatting with you about something near and dear to my heart, stellar winds. And it's doubly timely in the sense that you just put up beautiful pictures of the Crescent Nebula. And the Crescent Nebula is indeed sort of an example of some of the things I want to touch on here when I talk about stellar winds and their role in terms of that title that you see there, the givers and takers of life. And the Crescent Nebula is a great example of the sort of thing that I will touch on. One of the examples of the things that I'll touch on over the next sort of 40 minutes or so. Normally, when one is giving a talk on, let's say broadly calling it stellar winds and the things that blow off of stars, we typically, and the questions I get, whether it's school kids or the public, normally when we think of winds and things blowing off of stars, we think of things like this. We think of the really spectacular winds associated with exploding stars, with supernova, and this is an example of a little animation that, turns into the Crab Nebula. And yeah, that is an example of a stellar wind. It's an extreme example, and it really only applies to those last few minutes of the star's lifetime. And so if we just focused on the spectacular explosion process, you would end up ignoring all the different types of stellar winds that come along from the time the star is born through to those last few minutes at the end. And so that's where I'm going to focus. I will mention supernova a little bit here and there because it's hard to avoid it altogether. But the focus more is on the, if you like, the pre-explosion, the pre-supernova winds. How responsible are they for some of the things that we see around us, and that enigmatic subtitle, the givers and takers of life, and what role those pre-supernova, pre-explosion winds play in shaping both life forming and life ending, if you like. So that gives you sort of a broad overview of where I'm heading. And there is an enormous taxonomy, an enormous zoo of different types of stellar winds. And I'll just quickly touch on just a few of them right now before I delve into some of their applications, if you like. And different types of stars, whether they're low mass stars like the sun or really heavy stars that ultimately led to, for example, the Crescent Nebula. They have different types of winds at different points in their lifetime. And so we see the manifestation of these winds in different ways. So we start with a star, say, like the sun, very typical bog standard type of star that's sprinkled throughout amongst 100 billion or so in our Milky Way. And there's a stellar wind that is around us. Now, it's not a particularly, a huge amount of mass, if you like, that is leaving the sun, but it's still a wind. The particles are driven out by this hot magnetized halo, what we call the corona of the sun. It's hot, it's magnetized. That's the key point. And so high energy particles, charged particles, are able to escape the gravity well of our sun due to the incredible amount of energy that they're able to acquire from this hot magnetized halo. And so you get this steady stream, and yes, it waxes and wanes, and you get depending on what's happening with the sun at any given time, you get lots of sunspots. You may get lots of aurora borealis or australis, whatever the case may be. But that wind is always there. And those particles are being driven, like I said, by the hot magnetized halo. And so you have particles that are escaping that gravity well at pretty good clip. Hundreds of kilometers per second is the speed at which these particles are streaming away from the sun in this solar wind, or stellar wind, if you like. And it's driven largely because of the fact that corona is not only magnetized, but very hot, millions of degrees in terms of temperature. And that provides the energy needed, if you like, to boost those particles so that they can escape from the sun and work their way across the solar system, including washing over planet Earth. So that's one type of wind. Like I said, it's not a huge amount of mass that is leaving, but it's still an important component of the history of the sun, and it lasts for billions and billions of years. So that's one type of stellar wind. Changing, let's see. If you leap forward, say, 5 billion years from now, towards the end of the lifetime of a star like the sun, these lower mass stars, towards the end of their lifetime, they go through a relatively brief, it may last for many thousands and thousands of years, but in the grand scheme of many billions of years, that's just a drop in the bucket. But the rate at which mass is leaving through this stellar wind increases dramatically. And so stars like this one, this is a planetary nebula associated with the remnant of a lower mass star, and what you see towards the end of its lifetime. And you're losing not just handfuls of particles, you're losing a substantial fraction of the mass, sort of on the ballpark numbers is about a mass of the sun, a solar mass every 1,000 years or so. It's not blasting out at hundreds of kilometers a second. It's an enormous amount of mass, but it's sort of the wind is blowing out at a few kilometers a second. So you're down significantly in terms of the speed, but you're up significantly in terms of the amount of mass that's being pushed out by the wind. In this case, the wind is being pushed by radiation. It's not so much the hot corona of the star which is pushing it forward. It's radiation itself, the stuff that we see with our eyeballs, with our telescopes, with our CCDs. That radiation is strong enough that it's able to push against dust that exists in the outer atmospheres towards the end of the lifetime of the star. After it's gone through its red giant phase, as we just heard just a moment ago, you've got a significant amount of dust surrounding the star, and that radiation, again, it's not pushing it out at a huge amount in terms of its speed, but it's a substantial fraction of that atmosphere of the star is being pushed out. Like I said, roughly a solar mass every 1,000 years or so. So a substantial fraction of the star itself is being blown outwards, pushed by the radiation itself. If you move away from low mass stars, say like the sun plus or minus, to much heavier stars, the ones that ultimately do, if you like, explode as supernova, those ones that are 10, 20, 50, 100 times heavier than the sun, you sweep them under the title of a massive star. This is an example of one here. It's a 40 solar mass star, LL Orionis. And Orionis, it's also losing a solar mass, but it's losing it every million year or so, plus or minus. But again, it's being pushed out by radiation at a much higher speed than the planetary nebula that I just showed you in the previous slide, which was being pushed out at a few kilometers a second. These big massive stars, the radiation is able to push the wind at a much higher speed, still a substantial mass, a solar mass or so, and it's pumping out a solar mass every million years or so at a significant speed, thousands of kilometers a second. And the radiation, when I talked about the low mass stars, which aren't quite as hot, and so you get lots of dust and molecules that are pushed, the high mass stars, the radiation is strong enough that it can push sort of individual atoms, the atoms that are floating around in the outer atmosphere of the stars, atoms of carbon and nitrogen, the building blocks of life. They can be pushed out by that radiation at a substantial mass and at a substantial speed. And depending on whether you see this process of a high mass star blowing its wind at the early phases of the end of its life or towards the end phase, if you like. If you zoom in, you can see things like this is NGC 7635, roughly the same sort of mass as LL Orionis, 44 solar masses. And you can actually see a bubble that is being pushed out, driven by that radiation coming from the high mass star that's down in the center of this bubble. This is the scale isn't shown on there, but it's a really, really big bubble. So 10,000 times bigger than what we would call the bubble around our sun. And I'll come back to that one in just a second. And so that's a common sight that you will see around these high mass stars. Again, this is all before they ever explode as a supernova. You can see these big bubbles being pushed out, driven by that radiation pressure that exists. That's coming from those high mass stars that are pushing out lots of material at a high speed, driving these really, really big bubbles around the star that hasn't gone a supernova yet. So that is sort of some of the broad stellar winds zoo, if you like, and I'll touch on some of them as we go along. And so the main points of focus that I'm going to spend over the next 30 minutes or so boil down to this: the solar wind, and it's near and dear to our heart. I'll talk a little bit about this thing called the heliopause and why it's important. I will look on a slightly larger scale, still sort of around us, and look at this thing called the local bubble and how it ends up sculpting and shaping what we call the interstellar medium that surrounds us, our local neighborhood within the Milky Way. And then I'll move to larger scales, to galaxies as a whole. I will introduce something called, the details don't matter right now, what's called the overcooling crisis, and how stellar winds play a pivotal role in solving one of the biggest mysteries that has existed in computational physics, computational astrophysics, at least for the last 40 odd years or so, and how important those stellar winds are in avoiding this crisis. And then I'll end with a little bit on the chemistry. And again, normally when we talk about the chemistry and what the stars provide to the chemistry of the universe and the chemistry of the galaxy, we have a tendency to focus on those exploding stars, the supernova, which are responsible for an enormous fraction of the elements that you see on the periodic table. But it sweeps under the rug the really important role that the stellar winds contribute to that chemistry before a star ever explodes. So those are sort of the four key broad points that I want to focus on for the remainder of the talk. So let's start with the solar wind. It's a little cartoon. It may be hard to see depending on how close you are to the screen, for which I apologize. Down in the very little center there is the solar system and the sun. And you see various features identified. This broad bubble that's surround us, it's called the heliosphere. And again, that bubble is being driven by the solar wind that I talked about just a few minutes ago. And that bubble doesn't extend forever and ever and ever, because we are not, our sun is not sitting in isolation. We are surrounded by what we call the interstellar medium. Once you move far enough away from our solar system, you get into the background of gas and dust that exists all throughout the Milky Way. And so the bubbles that get driven by those particles that hot magnetized corona of the sun, which is pushing out this wind, eventually that wind runs into the surrounding interstellar medium. And that surrounding interstellar medium can be substantial in terms of the amount of material it has. And so the bubble doesn't grow forever and ever and ever. It eventually runs into the interstellar medium, the ISM, and the bubble eventually comes to a stop. It reaches a balancing point between how the bubble can expand driven by radiation, and pushing back is the interstellar medium, which stops that. And so you get this whole thing called the heliosphere. The sun is moving at the same time, so it's never always a perfect sphere, if you like. And you've got different characteristics in there, shocks and things, but the details don't really matter. Broadly, you have this whole thing, which is driven by the radiation, and the size is shaped by the surrounding interstellar medium pressure that pushes back. The important thing for what I want you to take away from that, it's more than just sort of a pretty picture. No, if you got good eyes, you may see both Voyager 1 and Voyager 2 in cartoon form drawn on there. Both of those satellites have left the edge of this bubble, this heliopause, the edge of the heliosphere. And so they're outside even the most extreme part of what we might call the solar system. But for our purposes, the main important thing here is that this heliosphere, it protects us from an enormous amount of damaging, not only radiation, but primarily charged particles. Charged particles are all around us, protons and electrons and other charged particles. Some of them are generated by the sun itself, as we talked about, but all of the neighboring stars and supernova and everything else around us in the galaxy also generates charged particles. And that heliosphere around us protects us. 90% of those charged particles that would come racing at very high speed and can provide irreparable damage to DNA are shielded from us by this bubble, the heliosphere that wraps around our solar system. So it's more than just an academic exercise to talk about the size of the bubble around the solar system. It does provide a really fundamentally important contribution to the development of life by shielding us from this 90% of these charged particles, which could have a damaging impact on the development of life on the surface of planets. And I will come back to this briefly in a few minutes. I step out a little bit further to what we call the local bubble. So say we've got a bubble that's blown by the sun, but all the other stars are blowing bubbles as well. And some of those stars are big, massive stars. So even ignoring supernova for the time being, you've got bubbles being pushed around all around our local neighborhood, and indeed throughout the Milky Way. And the local bubble is a very large, it's not a perfect circle in the way that you might, or spheres, you might picture a bubble being, but it is a region of our local part of the galaxy that has been evacuated by more than just the sun, but lots of neighboring stars that have helped push out the interstellar medium. Some of them push them out a little bit, some of them push it out a lot. And eventually those little bubbles can overlap, and you do get supernova. You don't just have stars blowing bubbles through the radiation pressure, but eventually you do get stars that explode, and they dump a lot of energy into this bubble. And because you have sort of pushed the gas around a little bit, loosened it up, if you like, making it what we call turbulent, when a supernova does go off, it's much more efficient in really clearing out the bubble that's been initiated by the stars blowing their own individual pre-explosion bubbles. But by loosening it up, making it turbulent, those odd supernovae that do go off in our local neighborhood are really efficient at evacuating the space. And so in our immediate region around the sun, we sit within this thing called the local bubble, which is about 10 times less dense than if you stepped outside the bubble into the surrounding, what we call ambient interstellar medium. There's a lot more gas and dust, about 10 times the density outside of the bubble as there is inside of the bubble. But that's gives you a little bit of a picture as to what our local environment looks like, largely shaped by all of the winds that have sort of loosened things up before stars exploded. The stars that explode provide kind of the icing on the cake in shaping this local bubble in which we reside. So I want to say a little bit more about the local bubble and talk about these bubbles on even larger scales, like our Milky Way galaxy. So this is one of the most overused images in all of astronomy, kind of the timeline of the universe in a single snapshot. And from the left, you have the earliest phases of the universe, this microscopically small universe, which has permeated by little quantum fluctuations. And ultimately, these quantum fluctuations are the seed for the galaxies that we observe today, which is on the right. So as you move from right to left, you're looking back in time 13.5 billion years or so. And in that early phase of the universe, and I'm not going to talk about what happened before or how it kickstarted, but we have the Big Bang, and the universe rapidly expands in a period of inflation for a few 100,000 years. During those first few 100,000 years, the universe is still relatively very small. It's relatively dense, and it's very, very, very hot. It's so hot that if you think of the chemical elements that might be around, say hydrogen and helium, let's just think about hydrogen. Hydrogen is a very simple chemical element. The most common, 90% of the atoms that are out there are hydrogen. Hydrogen is one charged particle, a proton, with another charged particle, electron, attached to it. And that's all really what hydrogen is. But if it's really, really hot, the electron, which has a negative charge, can't stick, if you like, to the proton, which has a positive charge. And so all of the electrons get pulled off. And so during that early phase of the universe, those first few 100,000 years, instead of having the normal hydrogen that we know and love, where the electron is attached to the proton, you have this sea of electrons that have all been pulled off. Not only the hydrogen, but all the electrons get pulled off of the helium as well. And so you have this thick fog of electrons all around you. And those electrons, and as well, they provide kind of a shield that stops the light, the energy that gets generated during the Big Bang can't actually move very far. It runs into all of this fog of electrons. And so when we look back in time, we can't actually see the Big Bang. We can't really see anything that happened in the first few 100,000 years after the Big Bang. We can't actually see because none of that light can actually move and escape. It just gets trapped by the fog of electrons. It's only as the universe continues to expand, and as it expands, it cools down and cools down and cools down. And then a few 100,000 years after the Big Bang, it becomes cool enough that fog of electrons, they can reconnect onto the hydrogen and the helium. And so the fog gets lifted, and then we can see the energy from the Big Bang. So we can't see it directly from the Big Bang, but we can see its remnants a few 100,000 years after the Big Bang. And you may have heard of this before. This is something called the cosmic microwave background. This is the furthest that we can look back in time and see. And what you would see is if you looked across the sky and looked sort of up in one particular place or looked over in another particular place, you would see teensy tiny little temperature differences. It would be a little bit hotter in one place in the sky, a little bit cooler in another place in the sky. And that radiation that we see, we don't see it with our backyard telescopes or professional telescopes. You see it with microwave detectors. But when you look and make a map of the entire sky with the different temperatures, as you can see there, what you're seeing there, those subtle little temperature differences, the little bits of red, the little bits of blue, those are the seeds for the galaxies that we then observe over the last 13 billion years, from the appearance of the first galaxies through to today. And there's an enormous amount of information encoded in those subtle little temperature differences that you can see. And those little, like I said, those little temperature differences, those are the seeds for the galaxies that we observe with our telescopes. And you can look at that mottled pattern of temperatures. You can look at how galaxies spin around. You can count the number of galaxies looking back 1 billion years, 2 billion years, 3 billion years. You can go back in time and just count them. All of that together suggests that about 15% of the matter in the universe, 1 part in 6, 1 part in 7 of the universe is made out of stuff that we know and love, the normal elements that we know, stuff that we're made out of, what we call baryonic material. And it also tells us that 85%, 6 parts in 7, if you like, is dark matter. It's mysterious, and I guess you've got a couple of talks coming up on dark matter and dark energy, and so you'll hear a lot more of that over the coming months with ASE speakers. That dark matter dominates how our universe evolves because there's just so much of it. We can't see it. I mean, we can't point a telescope at it and see it, but we can feel it. We can infer something about it through gravitational lensing and how it bends the light. And I know, again, you've got a speaker coming up in the autumn who'll be talking a lot more about that specifically. So we know that this dark matter dominates the matter content of the universe, but it only interacts through gravity. It doesn't give off light. It doesn't absorb light. It doesn't radioactively decay. The only force it cares about is gravity. And that's nice because gravity is really simple to model inside of a galaxy. So the vast majority of the universe, all you need is what we call the inverse square law. You know, as you move 2 times further away from something, the force of gravity doesn't go down a factor of 2. It goes down 2 times 2. It goes down a factor of 4. If you move 10 times further away from object, the gravity doesn't go down a factor of 10. It goes down a factor of 10 times 10, a factor of 100. That is what the inverse square law is. So it's really simple physics that you can put into a computer. And so this, you know, it's the first simulations that were done with computers, and I think Catherine Hammonds will probably talk a little bit about that next in a few weeks. If I take the cosmic microwave background as my starting point inside of a computer, and the only physics I put in is that simple inverse square law, I can generate something, say on the right, that the simulation that you see there, that looks remarkably like our present day universe. It has the filaments and the webs and galaxies and clusters in the right numbers in a statistical sense. Really simple to do. You just take what the universe shows you with the cosmic microwave background, put the simplest physics imaginable, and you get a universe that looks pretty darn good. And that's good, you know, that's good. The trick, though, is, and where people like me and others come in, is then drilling down a little bit deeper into the individual galaxies that we know and love, like the Milky Way, for example. And so can we take the simple inverse square law, the gravity that went into those universe-wide simulations, and can we generate things that look like not only elliptical galaxies, but dwarf galaxies and spiral galaxies using just that simple physics, gravity alone? And these are the first runs. This is what, 45 years ago, the first computer simulations looking at galaxies, where things were thrown together in different ways using just gravity, and then looking at what the outcome was. So top left is the beginning where 2 things were thrown together. They interact a little bit, and down at the bottom right is the final product. And what they found in those first simulations, no matter how they sort of threw things together and modeled it, if they just modeled using gravity, they ended up getting something that kind of looked like a blob, more like an elliptical galaxy, if you like, than a spiral galaxy. We didn't get things that looked flat and rotating with spiral arms, the sort of things that we think of when we think of grand design spirals like the Milky Way and Andromeda. And the main point to take from that is that carefully moving particles just using gravity, dead easy. And that is, 85% of the matter in the universe. The problem is you can't actually, like I said earlier, even though that dominates the matter content of the universe, we can't actually see any of that. So, the question is, does that simulation that I just showed you a minute ago, does that even reflect what you would see with a telescope? Because it only reflects dark matter. What you might observe with your telescope is not going to be the dark matter. It's going to be that 15% that's left over, the baryons that we are made out of. The problem is, and what we learned very quickly in the earliest generation of computer simulations, is that modeling the 85% dark matter, dead easy. Modeling the 15%, the stuff we can see, really hard. The baryonic physics, it's more than just gravity. It requires something called fluid dynamics, hydrodynamics. The problem is things like gas, which ultimately is what stars form from, is the interstellar medium is largely gas. Yes, gas feels gravity, but gas also can be heated up. It can be cooled down. It feels friction or viscosity. All of those things are much more difficult to program into a computer. And so we very quickly ran into a wall. But if you take a step back, I've talked about gravity being a really simple thing. It's the Newton's laws that are taught in A level here and Scottish Highers. But basically, if you wanted to go beyond just using gravity, you need to use the laws of fluids and how fluids heat up and cool down and move and how they change with temperature. And that all comes under what we call viscosity. And we encounter it all the time, right? You can, if you've got a glass of water and you pour it, sloshes around in a certain way. If you take some treacle or oil and you pour it into a cup, it'll slosh around, but it sloshes around differently because it's more viscous, it's thicker. It's still all the laws of fluids. But even though that's intuitively obvious, putting that into a computer and getting it right is really tricky, even though the physics, if you like, is well understood and taught at A level here in Scottish Highers in Scotland. So at least when you boil it down to that, it actually looks tractable and straightforward. And this is exactly what we've done and a number of other groups have done, including groups in Edinburgh. We let the vast majority of the particles in our computer simulation be dark matter particles. And those particles move around, but they only feel gravity. They don't slow down when it becomes into a denser environment. They don't speed up. They don't change their properties when you heat them up or cool them down. They only move through gravity. Very simple. The other 15% of the particles, we call them gas or fluid particles. And they do feel gravity, but they also feel viscosity. And that is what fluid dynamics and hydrodynamics is. And it's exactly the same approach that is done, for example, in fields like automotive engineering. If you're designing Formula One cars and looking at, trying to find the optimal design to minimize airflow over a vehicle, this is not done in wind tunnels anymore. It's done in computers using exactly this sort of technique. Aerospace engineering, there's any number, I can't remember if I've got a few more examples, but natural disaster simulations, if you're doing erosion simulations, environmental science, computational engineering, they all use a similar approach to fluid dynamics. And so this is what our group and a dozen other groups around the world did. They tried to capture the fluid dynamics to see if putting in that real viscous fluid dynamics would give you something that looked like a spiral galaxy. And this is what we had wanted to define. We combined the inverse square law of gravity with the laws of fluids. And this is what we hoped to get, was not only things that look like ellipticals, but things that look like this, the grand design spirals with nice spiral arms. You turn them sideways, they're nice and thin. Some have big bulges in the center. Some are effectively have no bulge in the center. But that was the kind of zoo of spiral galaxies, if you like, that we were hoping to capture when we put in that missing physics that existed in the first generation of computer simulations. And the first ones, it's only sort of 30 years ago that the first simulations were done using fluids. And what we got was something like this. It is a disk galaxy. It doesn't look like a beautiful grand design spiral, but if you turn it sideways, it is squished down. It is rotating around like the Milky Way, but it's a very stubby, thick disk. It has a big bulge in the center, no obvious spiral arms, but at least it's kind of spinning and doing things that spiral galaxies do. And you could go forward, up until even up to 10, 15, 20 years ago, all the improvements in hardware and software made things a little bit better, but you still got things that were too thick. There was still way too much stuff piling up in the center, making these gigantic bulges that you can see in the cartoons that are there right now. That fundamental mismatch between the spirals that we know and love and see in our local universe and what we were getting from the computer. We knew we were heading in the right direction by putting these laws in, but we weren't getting the right exact match. And I alluded to this already. What we needed to do, we had something that's called an energy crisis. Basically, gas that ultimately formed stars was funneling into the center of these galaxies, and it was piling up. The gas just kept coming in, piling up in the center, piling up in the center. So all the stars were forming in the center, and we were forming just way too many stars in the center. We needed some way to heat up that gas as it came in and push it away before it all turned into stars down in the center. most of the work went around trying to use supernova, that last little bit of those massive stars that we talked about at the beginning. When they explode, just like the precursor to the Crab Nebula, yeah, you get lots of spectacular things happen. They're an enormous amount of energy, the equivalent of a billion of the most powerful nuclear weapon on Earth is what the energy that you would get in a single supernova. So it is a lot of energy to play with. And that energy does push gas around, and the simulations that's been running there on the side, every once in a while you would see little bubbles appear, largely being driven by these exploding stars. And that was the way the field worked for about 20 years or so, was tapping into the explosion energy and using that to try to stop gas piling up in the center. What was missing was a recognition, which we talked about right at the beginning, is that stars that are much heavier than the sun, those 20, 50, 100 times heavier than the sun, they're also pushing out bubbles and material before it ever explodes. That was ignored until sort of 10 years ago or so. And that really was the secret to try to get things. And ignore the one down at the bottom. The main thing to take from this little cartoon on the plot on the top left, it's the amount of energy that a star kicks out as time progresses over a few million years. And what's labeled SNE, that's supernova, you can see after a few million years, a star explodes and it dumps a bunch of energy into the surrounding medium. But up until that point, there's still an enormous amount of energy that's being dumped into the interstellar medium by the stellar winds that we all ignored for many decades. And that was the ultimate secret that our group tapped into, was the fact that we had ignored an enormous energy reservoir that could heat up and push the gas before it all piled up in the center. And so by tapping into that energy from the stellar winds, the hope was we would get those, the things that I showed you at the top. Those two are observed spiral galaxies. And then the first simulations that we did, tapping into this missing energy source, gave us things that you see down at the bottom. Still not perfect, but they were, for the first time, things that actually looked like real galaxies. Using the stellar wind energy that had been neglected for decades was the real secret to putting simple laws of physics into a computer and getting something out that looked like the Milky Way or looked like the Andromeda Galaxy. And my student who was really driving this, Chris Brook, generated this plot at the time, which I think 6 of them are real galaxies and 6 of them are fake galaxies. So unless you are a real aficionado and can recognize your favorite galaxy in there, it's actually quite difficult to tell the real ones from the fake ones by just using that one missing bit of physics that had been ignored. So that they were the stellar winds were the secret to generating galaxies that look like the galaxies that we see in nature today. And then the last one I alluded to at the beginning was chemistry. These stellar winds, they're more than just the sculptors, if you like. This is a periodic table. It's a different way of presenting the periodic table that we know and like. It's color-coded, and it's color-coded by the astronomical source that is responsible. And in green are effectively the supernova, exploding massive stars. So things, chemical elements like oxygen and fluorine and neon, sodium, magnesium, aluminium, phosphorus. These are all chemical elements that largely come from exploding massive stars. And that's how these very popular nowadays periodic tables color code them as coming from exploding massive stars. But that it's not a fair way of doing it. And I've kind of alluded to that already. The green, and that is a big chunk of the periodic table in terms of the elements that we know and love. It really should be split into the elements that came prior to the explosion and not just lumped into the ones that got generated during the explosion. The winds, those pre-explosion winds, not only were they important for sculpting our galaxy, but they're actually important for contributing to a number of the chemical elements that you see there. And again, it's a messy plot. The gory details don't matter. But if I went along the bottom to say a star which was 12 times heavier than the sun and went up, all of those chemical elements, yeah, they come from the explosion process. Once they get to stars that are 20 times heavier than the sun and move further to the right, say 40 times heavier than the sun, 60, 85, 120, those areas that are shaded with the horizontal lines, those are all chemical elements that come prior to the explosion. So a huge amount of helium gets generated from stars that are heavier than 25 solar masses before the star ever explodes. A huge amount of carbon comes from 25, 30, 50, 60 solar mass stars, again, before they ever explode. That wind is able to push out an enormous amount of carbon. It pushes out an enormous amount of oxygen. It can do the same for nitrogen and some of the other chemical elements. And so they are more than just sculptors. There are some really important contributions to the periodic table that come prior to a star ever exploding. And again, a slightly technical detail, but it's work that one of my PhD students, Kate Womack, was doing. These are some stars, and vertical is the ratio of fluorine to oxygen. Again, gory details don't matter. And along the horizontal is the amount of oxygen. And all of the work that had been done up until this period of time using models of how these chemical elements form and associating them all with just exploding stars rather than including the wind component gave you the bottom curve, the solid line that went across here. We weren't able to understand why there were all these points up high in this plot because we thought all of the fluorine and the oxygen only came from exploding heavy stars. And what we realized at the same time as we realized the importance of shaping in using these winds to shape and sculpt the interstellar medium, we realized that an enormous amount of fluorine, for example, comes before a star ever explodes. And so the dash curve you see across the top takes into account the fact that you do get a lot of fluorine, an enormous amount of fluorine, before a star ever explodes. So it may be a detail that doesn't interest you in particular because it's just one particular element. But again, it solved one of those, I'm not going to say a big mystery, but one of those little mysteries that existed in the field. Again, all down to the fact that we were neglecting those important contribution of winds before a star ever explodes. So supernova are great, but there's a lot of cool things that happen before they explode. And so just to end in the last couple of minutes, circling back to where I start. This is a kind of a pet interest of mine. It's not my area of expertise. And it links back to a question about whether we will ever colonize Mars. And you might think, what does this have to do with anything I've been talking about? There are a lot of challenges if we do want to ever colonize Mars. No matter what Elon Musk may tell you, it's a challenge. And there's a lot of reasons for that. Different gravity, no food sources, no water sources initially. The soil is toxic. There's no atmosphere, so the radiation level is ridiculous. The psychological effects, how are you going to generate energy? The temperature is super cold. There's lots of reasons for why it's a non-trivial exercise. I've got a YouTube talk on a TEDx talk that I did a couple of years ago, which goes into more detail about some of these challenges. Or if you're interested, you can just, don't write that down, but you can just Google it and find it on YouTube. How does this link back to stellar winds? Well, it comes back to the fact that, there's life on Earth. We've got an atmosphere. We've got an atmosphere because we have a magnetic field. That's the only reason, really, that's effectively the only reason why we have an atmosphere is we have a magnetic field that acts as a magnetic shield. These charged particles that get accelerated from the sun and do lots of cool things, like give us the aurora borealis and australis. But they get, the magnetic field acts as a funnel, and it protects us. It's a shield that allows us to retain that atmosphere. If we did not have a magnetic field, we would not have an atmosphere, and we wouldn't have life in any way, shape, or form, let's say. And that's kind of the cartoon on the right. Cartoon on the left is Mars. There is no magnetic field, and so there's nothing to help you retain the atmosphere, and that's why Mars doesn't have an atmosphere. Probably in the first few 100 million years, probably had a hot enough core that it did generate a magnetic field, and so there probably was a little bit of water on the surface in that first few 100 million years. But as that cooled down, the magnetic field turned off, and the atmosphere very quickly, within a few million years or so, gets evaporated, gets blown off. So it loses its atmosphere at a rate of, you can read the number, about 1 kilogram per second. because there's no magnetic field to act as a magnetic shield. So this is why we have life here. Not only is it important for some of the reasons I just described, the atmosphere provides protection from not only these charged particles that evaporate the atmosphere, protects us from damaging radiation, things X-rays and gamma rays. That's why if we do have satellites that study X-rays, they've got to be above the atmosphere because the atmosphere protects us. You don't have that on the surface of Mars. And so again, this is a kind of a messy plot, and the exact numbers don't really matter. You can think of what is a full body CAT scan is number one in these units. If you spend a year in space, say like this, it's an old plot that Scott Kelly did. Spending a year in space is the equivalent of getting a full body CAT scan, every second day or so. So your DNA is taking quite a hammering, and there are some really interesting studies done with Scott Kelly and his twin brother, who's also an astronaut, but spent that year on Earth, and they looked at the damage that was done to Scott Kelly's DNA from his year in space, and not having that protection that the atmosphere provides. But that's nothing compared to going to Mars, and you can see the numbers. And just going to Mars, a Mars mission is something on the order of that's just going to Mars and coming back. It's not spending any time there. That's about like the equivalent of having 1,000 full body CAT scans. So what that means for your body, who knows? But you can anticipate significant genetic damage from having 1,000 full body CAT scans during that mission to Mars. And it also means once you get there, because there's no atmosphere to protect you, you continue to get blasted by this radiation. So if you do want to colonize Mars, if you do want to stay for any substantial period of time on Mars, you're not going to be able to live on the surface unless you have sort of meter thick steel walls around you. Likely you'd be subterranean because you'll need the protection of the soil to stop those X-rays constantly bombarding you. So this is one of those challenges that often gets swept under the rug when we talk about the potential for colonizing Mars. So I talked a lot about how stellar winds were important for the giving life from the chemical elements, but they can also end life as well if you don't have a magnetic field to provide you with an atmosphere. So let's just pull all this down to the final scorecard. Givers of life. Well, I started right at the beginning. I talked about this heliopause, the bubble that is around our solar system. It protects us from these charged particles that come in and cause damage, not only to our atmosphere, but to our own system. 90% of them get protected by the solar wind that we have. They do provide critical elements for the development of life, a large amount of oxygen, a significant amount of carbon, and some trace elements like fluorine as well. They all come through those pre-explosion winds. And they were the solution to the 15, 20 years that people spent trying to get spiral galaxies inside of a computer that looked like real spiral galaxies. The real secret, and one of the few things we can point to my group and say we were the first to do that, was identifying the energy associated with the winds before the star ever exploded. That was the secret that finally gave us realistic looking spiral galaxies inside of a computer. So these were all sort of the positives. And then in terms of the takers of life, that's where I ended. Those stellar winds, they have, unless you've got a magnetic field or a magnetic shield to protect you, they are very efficient at evaporating any planetary atmosphere for a planet that is sort of close enough to the habitable zone of the star. Unless you've got a magnetic field to protect you and to hold on to that atmosphere, it makes it very challenging to envision a way in which life could develop on the surface of those sorts of planets. Subterranean, maybe, because you do have protection then, but otherwise you kind of need an atmosphere to protect you, to allow any sort of complexity, let's say, in your life to develop. So I think that's more or less everything I want to say. Hopefully picked up a few new things along the way, maybe like I did as well, a new appreciation for the role that those winds play. They may not be spectacular like supernova, and they may not get the lip service that supernova get, but without them, a lot of these things that we see around us today and the things that I've just described to you would not be possible without those pre-explosion winds. So thank you very much again.
Thank you very much, Brad. That was really good, and that worked really well on the screen here in Edinburgh. I'm looking at your screen. I should probably look at the camera. That was really good. We'll move on to questions if that's okay. If you have time for that.
Sure.
Yep. So we'll ask some questions in the hall here. First of all, if you're on Zoom, if you want to put your name in the chat, and Peter will call that out. And if you're on YouTube as well, hopefully we'll have time for that as well. So, are there any questions in the hall? Yep. Nigel here.
Hi, Brad. It's Nigel Goodman here. Thank you very much for your talk. That was very, very good. I just wanted to ask, we seem to be, with the advent of the James Webb Space Telescope, to be discovering galactic shapes in the very early universe that we didn't think were possible. Could you speak to that in some way? Would stellar winds have something to do with that?
Yeah, so that's a great question. I think this is still very much a subject a little bit in flux. The rush to get, in particular, you go back a year in time, the rush to get that first press release out led to some misidentifications, and so I'm not going to dismiss it altogether. I would simply say that there were those of us who took a lot more of a cautious approach at the beginning when all the press releases came out saying, here's this massive galaxy, 400,000 years after the Big Bang. It's not predicted by standard models, blah, blah, blah. And so many of those earliest ones were retracted, but it has sort of stood the test of time. It's modified somewhat. But yeah, you do get some maybe larger galaxies that many had not anticipated being there. Now, I can also say that there were legitimate groups out there who had predicted that there were going to be some large galaxies early on. Maybe they hadn't done a statistical analysis, but it wasn't shocking to everyone that they were there, even if maybe some of the more popular papers were the ones that got cited as saying that this was. But we had a paper come out using a really large scale simulation where we had predicted massive galaxies, so 700,000 years after the Big Bang, rather than some of the ones that were showing up 400,000 or 500,000. Now that, to me, a couple 100,000 years might make a big difference to certain people, but I guess I didn't lose as much sleep over it as maybe some of the other more competitive groups did. But it is also true that, that capturing all of the physics in that early phase, I didn't talk at all about black holes and the role that black holes might play in seeding those first galaxies. And that's where absolutely the stellar winds play a role. But at that earliest phase, in those very first generation, the seed that probably, kickstarts things, it's not just the dark matter, but it'll be the massive black hole, which provides kind of a seed for the galaxy to form around, if you like. And so there's most of the work nowadays over the last 6 months or so, and the papers that I see crossing my desk are largely around implementing physics around black holes and the energetics of those first generation of black holes and how they might merge together and how efficient they are at pushing material away versus allowing material to accrete and build up that galaxy. So I think, I guess I don't lose any sleep over it. I think it was missed by some groups because we hadn't spent the amount of time on thinking about massive black holes and how they form in the early universe. And those probably do play a really important role in that first generation of galaxies. So I think it's, as I say, it's not the treatment of the dark matter. It's probably not the treatment of the stellar winds. They all play a little role in it. But it was how black holes in that earliest, a few 100,000 years post Big Bang, how they had kind of been more or less ignored. And now we realize, no, they probably do play an important role and probably do provide the the tool that allows those very first generation of big galaxies to form a little bit early, you know, a few 100,000 years earlier than maybe we had anticipated. So that would be my take on some. You can ask Catherine, and she'll probably say something completely different, but that's my take on it. That's my take on it.
Okay, thank you for that. Any more questions in the hall?
So continue with the theme of early galaxies and population 3 stars that must have been around there. Are there things that we're missing or possibly missing in the processes that created those? Because the takeaway from your talk seemed to be, as well as the great stuff about stellar winds, is that we often overlook some minor effect, which actually turns out to be the key to unlocking how things work.
Yeah, so but there's a lot of things I swept under the rug. In terms of realizing think of it this way. If I could take a giant cube around us inside of our galaxy and just look at how much energy there is and where that energy comes from, how much of the energy comes from stars churning up the interstellar medium, how much of that energy comes from the cosmic rays that are whizzing by us left, right, and center, how much of the energy comes from magnetic fields. Almost all of these simulations, including ours, ignore two of the, in our part of the Milky Way galaxy, they're split more or less 1/3, 1/3, 1/3. 1/3 of the energy comes from cosmic rays, 1/3 comes from magnetic fields, if you like, and 1/3 comes from the turbulence from, if you like, exploding stars. And it's called equipartition. The energy is split kind of between those three. Almost every simulation that's been done. Now, this is changing more or less in real time, but any of the simulations I've shown you of ours, for example, we've ignored 2/3 of the energy sources in the universe. We ignore magnetic fields and we ignore cosmic rays, and we lump everything into the turbulence being driven by stellar winds and the supernovae, if you like. We kind of sweep everything into that one pot. It's incorrect. But we hope that the way in which we have swept it all under the rug isn't too far from reality. By lumping cosmic rays and magnetic fields into exploding stars, we probably do get the total energy source correct, but they're probably coming out on wrong timescales. So the generation of magnetic fields and the generation of cosmic rays are really important energy sources for how galaxies thrive and evolve. And we cheat in our simulations, and almost every group cheats in their simulations by not including them self-consistently. So that is one thing that clearly, but this is being addressed in real time as simulations get better and better and better. These are being addressed in real time. So that thing which had been more or less, those two things which had been effectively ignored are being addressed now. We'll see how the field develops over the next couple of years. The very, very first generation of stars, as you rightly say, those population 3, POP3 stars, there's still a bit of a mystery as to, there's only hydrogen and helium around when they first form. And the stars that form in that very first generation, they don't have carbon and nitrogen and oxygen, all the other chemical elements that we know and love. And that means that they evolve differently. They form differently. We ignore that, and most people ignore that. Again, there's almost a disconnect between those who work on the very first generation of stars and those who work on everything that happens thereafter. So I would sweep the formation of the very first generation of stars in with the very first generation of massive black holes. I think those are the two critical things which we're scratching the surface now of both of those. And I think, I don't think there's anything else massively missing, but there's a huge amount of work that needs to be done on the first generation, and whether they're all high mass stars, low mass stars, intermediate mass stars, what type of stars form when you only have hydrogen and helium, and as well, what do those very first generation of black holes look like? How did they get seeded? How do they merge? How do they grow to become bigger black holes? Those are things that we did a very poor job or effectively ignored in our simulations. We still got things that looked pretty darn good. They're not perfect, but they looked really good. But I think those are the two key things that are really, when I look at all the papers coming out, and they're largely focused around those 2 points, the very first POP3 stars and the very first generation of black hole seeds, if you like. That's the big unanswered question, and the things that if we've got it right, it's a miracle, because we've not really done those properly and had to cheat a little bit.
Good, thank you. Any more questions in the hall? Yep.
Hi, when you're talking about the different types of solar winds, you mentioned that stellar mass stars would blow off dust in the outer atmosphere. Dust to me implies heavier elements like silicates and such like. So is that dust actually nuclear synthesis in the star, or was that dust that was already in the system when the star was born?
Yep, it's because the outer atmospheres, so you don't get the same molecules and dust around the high mass stars because the radiation blasts them apart before they ever get a chance to. But the outer atmospheres of those, the stars that ultimately end up their lives as planetary nebula, they don't have the same damaging effect from radiation to blast apart all of both molecules. So you get more molecules, which means you're able to build up dust in different ways. The temperature is lower, and you just don't get that around high mass stars. The conditions are just not conducive for, particularly for dust to survive. That's probably not 100% true. There is some evidence that there is dust associated with supernova. It doesn't all get destroyed during the explosion process and the pre-supernova wind process, but the winds and the energetics associated with the planetary nebula are such that the cooler temperatures, the outer atmospheres, that material can survive the process of being pushed out by the radiation in a way that they can't around the high mass stars, broadly speaking, not perfectly, but broadly speaking.
Okay, I was thinking that the smaller mass stars couldn't actually generate those higher order elements, that they tended to stop at the carbon cycle or just beyond that, but can actually go more. I guess maybe their contribution's smaller.
You can during the phase when they're on, like our sun burn, on the main sequence, converting hydrogen to helium largely right now, generating the heavier elements right now is more challenging. As you get towards the end of the lifetime of the star, you end up having lots of neutrons floating around, because whenever you burn hydrogen into helium and helium into carbon and oxygen, you create neutrons, and then you get something called neutron capture. And so you're able to synthesize heavier and heavier elements by capturing neutrons and building up heavier and heavier elements. So even the low mass stars that you don't think of as being capable of synthesizing heavier elements, while they don't synthesize elements in the same way that the high mass stars do, they have phases in their lifetime where they are able to build some heavier elements. Now, things like silicon gets synthesized in high mass stars. So if you do have silicon associated in the outer atmospheres of a low mass star, it's not been synthesized inside the low mass star. It's left over from the material out of which the star formed. You're absolutely right in that sense.
Thank you.
Do you have one more? No? Is there any questions on Zoom?
No, I think we're questioned out at the moment, Mark.
Okay. Will, anything on YouTube?
No, no questions on YouTube. Excellent talk.
Okay, well, can we thank Brad again for that excellent talk? Thank you very much.
Thank you yet again for having me. I'll make up for it. I'll make up for it next year. I'll come up on my own expense and see you guys. I owe you a face-to-face. So thank you again very much. I appreciate
That
it.
would be great. Look forward to seeing you then. Okay, thank you. Okay, we'll have the slight break while Nigel sets up now, and we're going to have the sky in July.
Okay, thank you very much. We've got something coming through here. There we are. I'm going to talk to you this evening about the sky in July. I keep doing this to myself. I keep volunteering to do a sky in the month talk when there's no astronomical darkness around, but here we go again. So this is the sky in July, and this is a lovely image by John of noctilucent clouds. And that's the first element that I was going to talk about. June and July are the two main months in the Northern Hemisphere for the appearance of noctilucent clouds, noctilucent meaning night shining. And we'll come to talk about those in a moment. But also in July, we are very, as was mentioned with Alan Pickup's excellent report on the sky in July, that the planets make a welcome return to our skies. Also, again, as Mark mentioned, are we going to have a nova? And might we have it in July, or certainly maybe before the end of the year? But there's a strong possibility that in July, the blaze star, as it's called, could go nova, and we'll take a look at that also. And finally, there's a comet, which when I was reading about it, comet 13P Olmers, when I was reading about it, I'm thinking to myself, well, it's kind of low in the sky, and this is a theme for a number of the things that are going on in the July sky, as well as the lack of darkness, is that they're quite low. But then I thought to myself, well, of course, we now have the ability to look at the sky from a much lower latitude in northern Spain. So a lot of these things that are quite low for us here in Edinburgh are still well within the grasp of our telescopes at Trevinca. So I mentioned the lack of darkness, another image by John of the early evening sky in the summer of Edinburgh with the accompanying clouds. So there's a lack of true darkness, which is not ideal for us astronomers. We are past the solstice, so the nights are getting longer. The nights are drawing in, as we say in Scotland. But let's just take a look at the month and see how this is changing. And we can see immediately that the daylight length is shortening as we go into, from the beginning of the month. We're shortening by, what's that? about half an hour or so. So by the end of the month, we're looking at perhaps quite a difference in terms of day length. And we are, because we're not getting true darkness, it's twilight. Most of the hours of darkness are actually twilight rather than proper darkness. And it took me a while to get my head around this, so I did a little explanatory diagram of how this actually works. If you're in this web page and looking at this data, you can actually expand each of these days. So, for instance, this one for the 31st of July. First of all, astronomical twilight is round. I don't know if you can see my cursor. Yes, astronomical twilight obviously is in the early part of the night on the 31st of July, and it then goes into nautical twilight as the sun is beginning to rise towards actually coming up above the horizon. So we move into nautical twilight, and then we move into civil twilight, and then we obviously have sunrise after that point. And then the process goes into the other direction. As evening comes, we have sunset at 21 minutes past 9 on that day, and when we move into civil twilight after sunset, and then after a period of time in civil twilight, we move into nautical twilight, and then back into out of nautical twilight into astronomical twilight. So that's how that data is. It seems a bit odd to me, but it actually is. It does work once you get your head around it. So that's the process that's happening, and the upshot of all that, the take home, as it were, is that although we are still have twilight nights, they are getting darker. I mentioned noctilucent clouds, night shining clouds, and here's a lovely image from Ian Smith out in East Lothian of night shining clouds, and we can see the ordinary run-of-the-mill clouds in the foreground here, but up in the higher atmosphere we've got these night shining clouds, which I mentioned are best in June and July in our northern latitudes. They are actually clouds of ice particles at extreme heights of something like 82 kilometers above the surface of the Earth. And what they're doing is they are catching the sun's rays, which the sun is by this time well below the horizon, but because these clouds of ice particles are so high in the atmosphere, they still get this ethereal reflection of light. They're very beautiful things to look at. And they're usually visible anywhere between 90 to 120 minutes after sunset in the northwest horizon, or before sunrise in the northeast horizon. It's a good time of year because to observe the sun, and this is a very nice image from Ramsay. This sunspot group here is the sunspot group that was responsible for the tremendous aurora borealis that we had a little while ago. And we are now currently in solar cycle number 25, which means it's the 25th solar cycle, which lasts for about 11 years since a extensive recording of sunspot activity began in December 29. It began at the present. I've actually covered that up. So it was in the 18th century that we started looking at solar cycles, and this is the 25th solar cycle since those records began. And this present cycle began in December 2019, and it's expected to continue. We're almost at the height of it. It's expected to continue until about 2030. And we can see here, we're reaching the peak, which should be sometime in 2025 and into 2026. we should be expect the maximum amount of activity from the sun. And certainly the sun has been very, very active over the last couple of years. One of the things that I've been absolutely amazed I've been involved in the Society now since 2019, but it's quite amazing what our astronomers are doing in the Society in terms of looking at objects like the sun. We have here a beautiful image from Robert Arnold, which is the sun photographed using a calcium K filter, which is, my understanding is that it's in the ultraviolet end of the spectrum. So you get this beautiful purplish look to the face of the sun, and you can also see detail on the face of the sun that you wouldn't normally see in white light. We've also got an image here from David Brett using a quark by a company called Daystar, which allows an ordinary telescope to be used to record hydrogen alpha, and that allows you to see much more detail on the surface of the sun and also prominences. And again, these are a couple of images from Robert Parsons, again both in hydrogen alpha, and it's just breathtaking, the kind of detail we're getting from solar images. So you can do some very interesting and beautiful work still in the summer without having to have astronomical darkness. Let's look at the sky. I've used the sky maps that Alan produces to give a simplified look at the layout of the constellations. This sky map is good for 0100 British summertime on the 1st of the month, midnight on the 16th of the month, and 11 o'clock on the 31st of the month. And we're looking north here, and we can see that the circumpolar, unsurprisingly, the circumpolar constellations are very prominent and very high. Ursa Major, the Plough, is dipping down towards the west in its yearly run round the North Celestial Pole. Cepheus, the two Cepheus, Draco, Cassiopeia, Canis Venatici, and all these types of a constellation, which are absolutely replete with deep sky objects, although some of them may be difficult to observe or photograph because of the twilight conditions. But there's a lot of stuff in there, and too much for a 10 or 15-minute presentation. But we're all familiar with these constellations in terms of the kind of treasures that they hold, one of which was shown in Brad's excellent talk, the Bubble Nebula in Cassiopeia. Capella and Auriga is much lower down in the north, whereas the Andromeda Galaxy in Andromeda and Triangulum are beginning to rise as the nights get darker. So these are some of the treasures that we can be looking forward to in the next few months. Some of the brighter deep sky objects at the darker parts of the night, which at the moment are in the wee small hours, might still be, with proper filters, might still be possible to observe or to photograph. This is M31, image by Mike McGovern, and Pat Devine's image of Bode's Galaxy and the Cigar Galaxy, M81 and 82, which is near the Plough. So these are two iconic images from the northern sky. Looking south, we've got Cygnus is very prominent, high in the southeast quadrant of the sky, with Lyra, and we can see the summer triangle, what's known as the summer triangle, made between the stars Deneb, Vega, and Altair. And that whole area, because it's the Milky Way runs through that part of the sky, is a fantastic hunting ground for deep sky objects, as is Ophiuchus, Aquarius, and Serpens. But some of the constellations that we don't tend to see too often in these latitudes, Capricorn, Sagittarius, and Scorpius, are also they're creeping up there a little bit higher. And certainly from northern Spain, we'd be able to access them quite readily. So looking at some of the objects like M13, M11, and the coat hanger asterism, which used to be called Brooch's cluster. It isn't actually a cluster. It simply looks like a cluster, but it's all the stars that are form what looks like the cluster are actually hundreds of light years apart from each other. It's just a line of sight effect. But the way they as we'll see in a moment, the way they appear from Earth, they look a bit like an upside down coat hanger. And here is that same object. Again, another image from Pat Devine, where he's flipped it so that it does actually look like what we would call a coat hanger. Also, from Hugh Somerville, the Ring Nebula in Lyra, again, is another excellent object. Quite a bright object, so it should be possible to see and also to photograph even in our twilight skies through July. And the Wild Duck Cluster M11, this is an image from Peter Black. And M13, the Globular Cluster, by some guy I haven't seen before, and that's in the Hercules, and also the Dumbbell Nebula. This is from our Zero telescope in Spain, which is a beautiful object, also in that part of the sky. Okay, T Corona Borealis, as Mark mentioned, we're all waiting with bated breath. We're monitoring Corona Borealis, the constellation, and this is the location of where it might actually go bang. It's a recurrent nova, as Mark mentioned, that tends to have this outburst, this explosion, roughly every 80 years. It's actually two stars, a red giant and a smaller white dwarf, orbiting each other. And the red giant emits a lot of hydrogen, which ends up on the surface of the white dwarf. And this heats it up to a critical temperature, triggering a massive explosion, but one that doesn't actually destroy the white dwarf. Hence, it's a repeating cycle. But as Mark said, that's something that should be obvious to people with telescopes. It may not be obvious to people who just glance up at the night sky, because it'll just be a new star rather than a blazing star, even though it's being called the Blaze Star. But we'll wait and see what happens. The moon in July. This is a lovely image from Mike Christie of the moon. And we've started a new project in the ASE, the Moon Project, which is gaining a lot of attention. These are the phases for the moon through July. Tonight is new moon, and our first quarter moon is on the 13th of July, mid-month. Full moon will be on the 21st of July, and the last phase, the third quarter of the moon, will be on the 27th of July. I mentioned the Moon Project, and here are just some of the images of the moon, which are, again, quite breathtaking in terms of their detail and sophistication. These two were taken using the Zero telescope. John Briggs was responsible for processing these. And you can see the level of detail is just immense. The moon is a fascinating object. It's always changing. And one of the latest aspects of the Moon Project is we're going to be trying to hunt down and image lunar lakes. We've all heard of the mares, the lunar seas, and the craters, obviously, and the mountains, but there are quite a few lakes up there. Not real lakes, but certainly objects called lakes. So again, it's something good to get involved in. And the moon, even in our twilight skies, can even be imaged during the day. The planets. The planets are morning objects in July for the most part. You'll have to be an early riser to make the most of them, because the best time to see them is around about 4 o'clock in the morning, just before sunrise. And again, most of them will be reaching decent altitudes towards the end of the month. Mercury at the moment is very low on the horizon after sunset, so it's difficult to observe from Edinburgh, but that may be a different case in point from Spain. And Venus at the moment is lost in the sun's glare. Mars and Uranus, however, on the 15th of July, will lie only 3 minutes of degree apart, quite close to, in the pre-dawn light, quite close to, in Taurus, quite close to the Pleiades. So they should be something that it's possible to get an image of or to see. And where I've got the little red circle there, it's actually going, the planet Uranus is actually much closer to Mars than that, but that's about, I just wanted to give you a rough idea of where in the sky that would be. And that's about 25 degrees altitude. So if you are looking towards the east in the pre-dawn, that might, you can find the Pleiades and use them as a signpost to find those 2 planets. And also in Taurus, this time quite close to the moon, in the east, we will find Jupiter. And again, we can use both the head of the bull in Taurus and also the moon as a signpost to finding Jupiter. And again, that's reaching a decent altitude towards the east. This is again in the early pre-dawn hours on the 31st of July. And Saturn, Saturn will be quite high in the sky towards the south, over 25 degrees at the end of the month, again in the early hours. The rings, however, will be hard to see because their inclination towards us in terms of line of sight is only 2 degrees. So we're rapidly getting to the point where they will, at least for the time being, effectively disappear from our view. Comets and asteroids. I mentioned comet 13P Olbers. It's currently in the constellation of Lynx, at a distance of 289,000 kilometers from Earth. It will reach a magnitude, should reach a magnitude of 7.5, and ends the month in Ursa Major. So that's the current position of the comet at the moment. It will have a bit of a tail, but comets are tricky things. But that, again, that's something that should be trackable by the Society. It's a periodic comet, has a period of 69 years and was last visible to us in 1956. The asteroids, I'm just going to concentrate on one Ceres, which is actually a dwarf planet, designated as a dwarf planet, and it's the largest of the asteroids that we currently know about. It will reach opposition on the 6th of July, very low in Sagittarius from Edinburgh, but again, it's something that might be spottable from Spain at a magnitude of 7.3. And this is its track through the month, starting round about here, in just to this side of the teaspoon and teapot asterism of Sagittarius, and then working its way down that way in Sagittarius. It will pass by the bright star Ascella in Sagittarius around about the middle of the month. Meteor showers, there's a few, obviously because it's so light, difficult to see. The Alpha Capricornids will peak on the 30th of July. They have a low hourly rate and they will be low in the south, and they generally are made up of yellowish, slow fireballs, but you might spot some of them. And the Delta Aquarids also peak at the end of the month, a bit of a better hourly rate of 25, lowish in the southeast, and should be a steady stream of meteors. And although it's not strictly speaking a July event, the Perseids, although they peak in August, but they may start as early as the 17th of this month. And they usually consist of bright, fast meteors. So who knows? And here's an image from Mark of a Perseid meteor. I'm not quite sure when you took that picture, Mark, but it's something to look out for. We might get our meteor group might pick up something on their cameras. And that's it. Thank you very much indeed for your attention.
Thank you, Nigel. Very comprehensive. And considering you said there was nothing in the sky because it's July, that's quite a lot of stuff. I'll take that. That's fine. Okay, that's it. From the front, we have tea and coffee, bickies afterwards, provided by Peter. Thank you, Peter, as always. We have to be out by 10 o'clock, but there's lots of time to hang around for chat. So see you online in the middle of the month when we'll have Catherine Hamans talking to us. So thank you very much.